Unlike previous sections where each individual section had a video, this chapter is only going to have a single video. And the reason for that is that I've kind of combined some of the ideas in the different sections into a single video, so I will make those sections also available so you can see them. But I'm also skipping some of it as well. The main thing that I'm skipping is naming molecules with different functional groups. That is one of the early things that you'll talk about in organic chemistry chapters when you talk about different functional groups, or in some textbooks they'll put all the naming at the beginning of the book even. But here I thought it was a better idea to bring them together so you can see these different functional groups as a collection of functional groups instead of as individual chapters. I just think that works better. So one video for this entire chapter. So what we're talking about here is organic chemistry. And I think everybody's heard of organic chemistry, but not everybody knows it is the chemistry of carbon. Okay, so carbon is a unique element in that it can form many different things. That's not to say that other elements can't form many different compounds, but carbon can form a wide array of compounds. And here are just a couple of examples. So this is a carbon-containing molecule. So this represents a carbon, and this represents a carbon, along with some oxygens and some hydrogens. And when you put them together in this way, you get aspirin. And aspirin, as you know, is a pain reliever. Many pharmaceuticals, the vast majority of pharmaceuticals, are organic molecules. So this is just one example of a pharmaceutical, aspirin, that is an organic molecule composed of carbon. Polyethylene is a polymer of carbon and hydrogen. Okay, this N means there could be a lot of them, 1,000 of them or whatever the case may be. And polyethylene is used to make plastic. Polystyrene, which is used to make styrofoam, is just a different hydrocarbon compound. Or polyvinyl chloride, which is a hydrocarbon and it contains chlorine as well, which makes PVC, polyvinyl chloride. So plastics are made of carbon molecules, quite different than aspirin, right? Functionally, they're quite different. Even though they're both made of carbon, the materials themselves are very different. Protein. So this is an amino acid, glycine, the simplest amino acid. And there are a bunch of other amino acids that are composed of, that humans are composed of. But in this case, glycine is one of the amino acids that makes up proteins. And here I give an example of, a protein you could buy, but protein also makes muscles, okay? And what about your base pairs that make up DNA? Well, here's adenine, just one of them. And this is one of the molecules that makes up DNA, again, a carbon-based molecule. So DNAs, RNAs, proteins, pharmaceuticals, plastics, the stuff in gasoline, hydrocarbons, methane that is burned for fuel. Hydrocarbons and carbon-containing molecules make up lots and lots of different things, and this is why organic chemistry is, a field unto itself. And that's what we're going to talk about a little bit in this chapter. Needless to say, we're not going to get through a lot of organic chemistry in this, whatever it ends up being, 30-minute lecture. Okay, so one of the things that I want to remind you about, and this is covered more strongly in section 7.3, which is based on Lewis structures. If you have downloaded the files, you can just click this link to get there, is formal charge. And in a Gen Chem textbook, it'll tell you formal charge equals the valence electrons minus half of the binding electrons minus the lone electrons. And if we do formal charge this way, organic chemistry will be challenging because it takes forever to calculate formal charges this way. So what we're going to look at is comparing the electrons around an atom, the dots and the dashes, to the number of valence electrons that an atom wants. So let's look at an example of this. In an organic book, you may see methylamine represented in this way, okay, where you have the CH3 and N2H's. In reality, this nitrogen is neutral. If you were to look at this nitrogen, you would say, well, nitrogen wants 5 electrons, count the dashes as 1. It has 1, 2, 3 electrons around it, so therefore it's plus 2. But in an organic chemistry book, and this is in every organic chemistry book or even in a single organic chemistry book, not in every structure that's drawn, but oftentimes they'll leave out lone pairs. So for atoms other than carbon and hydrogen, you can assume that they have an octet. So in this case, we have to assume that nitrogen has an octet. So it doesn't just have 3 pairs of electrons, it actually has a lone pair. So now nitrogen wants 5 electrons. How many does it have? 1, 2, 3, 4, 5. And this nitrogen is neutral. Note that carbon wants to have 4 bonds. And carbon is bonded to 3 hydrogens and a nitrogen, so it is also neutral. Let's look at acetic acid, okay? Acetic acid is the stuff that you find in vinegar, and it might be shown this way in an organic chemistry book. If you notice here, this oxygen and this oxygen don't have octets. So, in order to fill their octets, we can assume that this oxygen has 2 lone pairs plus the 2 bonds. That gives it an octet. And this oxygen also has 2 bonds, one to this carbon and one to hydrogen. So it also has 2 lone pairs. Now, if we look at the formal charge, oxygen wants 6 electrons. Count the dots as 1, count the dashes as 1. It has 1, 2, 3, 4, 5, 6. Wants 6, has 6. It's neutral. This oxygen wants 6, has 1, 2, 3 with the bond to hydrogen, 4, 5, 6, wants 6, has 6, it's neutral. This carbon has 1, 2, 3, 4 bonds, it's neutral. This carbon has 3 bonds to hydrogen plus this one extra bond, it is also neutral. So even though these look like incorrect Lewis structures because they don't have octets, these are not uncommon in organic chemistry textbooks. In fact, they actually, as you'll see a little bit later, get into things like skeletal formulas and things like this where there's even less written. And the reason they do this is they're drawing so many structures that they don't want to have to constantly write in all the electrons. I mean, that's my guess. Or they simply just assume that we know they're there. I don't know the exact answer to that question. All right, so let's take a look here at some atoms that may have formal charges. So it says identify the non-zero formal charges in each of the following, and these are again written in organic chemistry notation. So note that for carbon and hydrogen, we don't always show lone pairs if we have, we just assume that they have octets. So if we look at this oxygen here, it has 1, 2, and the third bond to hydrogen, which means it doesn't have an octet, so it does have a lone pair, like that. So if we look at the formal charge on this oxygen, it wants 6, has 1, 2, 3 to hydrogen, 4, 5. It's missing an electron, so this is plus. This carbon has 4 bonds, 3 to hydrogen and 1 more. 4 bonded carbon is neutral. This carbon is the same. How about this carbon? 1, 2, 3, 4 bonds. 4 bonded carbon is neutral because it wants 4 electrons around it. Let's look at this example here. Well, carbon has 4 bonds, 3 to hydrogen and 1 to the nitrogen. How about the nitrogen? Does it have an octet or does it need a lone pair? Well, if we look at nitrogen, it's got 2, 4, 6, 8 total electrons around it, so it already has its octet. Nitrogen's in 5a, so it wants 5 electrons, 5 valence electrons. How many does it have? Dots is 1, dashes is 1. 1, 2, 3, 4. So it only has 4 electrons, so it's missing an electron, so it is also plus. Let's look here at this structure. First, let's look at atoms other than carbon and hydrogen and see if they need octets. So if we look here, oxygen has 2 bonds, so that means it must also have 2 lone pairs to have an octet. And this oxygen only has 1 bond, so it must have 3 lone pairs to have an octet. Carbon wants 4 bonds, has 3 4 bonds. This carbon also wants 4 bonds, has 1, 2, 3, 4 bonds. It's good. Now, for oxygen, oxygen's in 6a. It wants 6 electrons around it. Count the dots as 1, dashes as 1. It has 1, 2, 3, 4, 5, 6. Wants 6, has 6. It's neutral. This oxygen wants 6 also because it's in 6a. How many does it have? 1, 2, 3, 4, 5, 6, 7. So it's minus. Okay. The last one, we have carbon here. And this carbon has 4 bonds, 3, 4. This carbon has 3 4 bonds. And this carbon has 3 4 bonds. What about this carbon? This carbon only has 3 bonds. Now, we're not going to assume that carbon has an octet. In fact, we're going to assume in this case that carbon doesn't have an octet. So carbon wants to have 4 electrons around it, has 1, 2, 3. It's missing an electron, so it is positively charged. Now, in this section, I'm basically reviewing, assuming you already know how to do this. If what I'm saying doesn't make a whole lot of sense, go back to section 7.3, and there's a more in-depth explanation of how to identify where the plus and the minus charges are. Being able to identify where plus and minus charges are in organic chemistry can be very useful in understanding what's going on. In fact, I would argue that it's essential for understanding what's going on. The other thing is you're going to start to see patterns. So if you see nitrogen with 4 bonds, it's always going to be plus. If you see oxygen with only 1 bond, it's always going to be minus. If you see oxygen with 2 bonds, it's going to be neutral. And if you see oxygen with 1, 2, and then 3 bonds, it's going to be plus. Now, trying to memorize those rules and not know how to calculate the formal charge of everything that is presented for you, I think is a harder way to do it. I think it's easier to understand how to calculate the formal charge of anything that's put in front of you, and then your brain will start to see patterns. So I just look at this and I know this oxygen is minus, or I just look at this and I know that this nitrogen is plus. But it takes practice to do that. It doesn't just happen instantly. And if you try to just memorize this as a bunch of rules, I think that it's more problematic than just understanding how to calculate the formal charge quickly, so that when you're stuck, you can just double check. Did I remember that rule right? You can just quickly double check and get the formal charge of the atom. All right, so the next thing that we want to talk about after we do the review is alkanes. And alkanes, okay, are hydrocarbons of the general formula CnH2n plus 2. What this means is for every carbon I have twice as many plus 2 hydrogens. So if I have 3 carbons, I have 2 times 3, which is 6, plus 2, or 8 hydrogens. So if I look here, C3H8. All right. So this is propane, the stuff that you use in a barbecue grill. All right. Methane, which is the most abundant form of, the most abundant molecule in natural gas, is simplest with 1 carbon and 4 hydrogens. If you have 2 carbons, okay, you then have 6 hydrogens. That's called ethane. If you have 3 carbons, you'd have 8 hydrogens, propane. The stuff in Bic lighters, 4 carbons and 10 hydrogens, is called butane. Pentane, like the pentagon, has 5. Hexane, like a hexagon, has 6 carbons. Heptane, 7. Octane, like a stop sign, an octagon, has 8 carbons. Nonane, 9. And decane, 10. We're not going to go up to these higher numbers. Another thing to notice, it's just interesting common knowledge and not super important for this class, is that once you get to 5 carbons or more, they become liquids. And once you get to 14 carbons or more, they become solids at STP. At room temperature, you need about 18 carbons for this to be a solid. Of course, room temperature varies slightly. These solids would be waxy type solids, okay, that you would find if you have 18 carbons or more. But the smaller ones are gases, and you know this because methane is the major component of natural gas, or propane on a barbecue grill is a gas, all right? And then they start to become liquids. Also note that the number of structural isomers. So what we're going to talk about here is the number of different things that carbon could make. So if you look here, if you take the formula C18H38, this is molecules that contain 18 carbons and 38 hydrogens, you can make 60,500 different versions of molecules that contain 18 carbons and 38 hydrogens. That's quite amazing that there is that much diversity in a molecule that isn't that big, right? I mean, it's only got 18 carbons. It's not the biggest molecule in the world, and there are still 60,000 plus combinations that can be made. So this starts to show you some of the diversity that can be made even in a single molecule. Now, is someone going to spend their time to make 60,000 different isomers of this? No, because they're probably not very useful. This thing would probably be burned. It would be its primary use, okay? That being said, there are lots of other things, like you can make aspirin, which is different from ibuprofen, which is different from any other type of drug, and these things are primarily made of carbon, hydrogen, oxygen, nitrogen, occasionally some other atoms. Okay? So the diversity here is what's important. What the take-home message from this slide is the names. This is something you absolutely have to be familiar with, is these names. Meth is 1, eth is 2, prop is 3, but is 4, pent is 5, and then there are different alkanes, so they end in ane. What we're going to talk about in this section is how do we name these different compounds, okay? And we're going to use these base names. Said another way, you're going to want to have access to this chart, you know, if you're taking a test or if you are doing homework or whatever the case may be, until you have them memorized. Okay, so let's look at some different representations of these different molecules, and I'm going to start with ethane because methane is so simple that you can't really do a lot with it. You'll see these two are the same and there's nothing down here. All right, so ethane could be represented this way. This is called the molecular formula, C2H6. So there are 2N plus 2 hydrogens. So 2 times 2 is 4 plus 2 is 6. So for every 2 carbons, there's 6 hydrogens. We could write this as a structural formula, which is CH3 bonded to CH3. We could write this as the expanded structural formula, where we actually show the molecules being this carbon is bonded to 3 hydrogens and a carbon, and this carbon is bonded to 3 hydrogens and a carbon. We can also show the skeletal formula, and here this is a little iffy, but this is a CH3 and this is a CH3. In the case of propane, the skeletal formula is more clear. This is C3H8. The structural formula is CH3, CH2, CH3. So we have this carbon bonded to 3 hydrogens, this carbon bonded to 2 carbons and 2 hydrogens, and this carbon bonded to 3 hydrogens and a carbon. If you note here, what's the reason for these structural formulas? Every single carbon here has 4 bonds. So if a carbon's bonded to one other carbon, it's bonded to 3 hydrogens. If it's bonded to 2 other carbons, like in the case of this middle one, it's bonded to 2 hydrogens, so that it can have a total of 4. Here we have the skeletal formula, and this is probably the smallest one where a skeletal formula makes sense. This doesn't exactly make sense. But here we have CH3, CH2, CH3. So at each point on this skeletal formula, we're representing a carbon and the appropriate number of hydrogens such that the carbon has 4 bonds. Let's look at a bigger molecule where isomers are actually possible. So here is the smallest molecule where we can have isomers, and this is butane, which is found in like a Bic lighter. So here we have C4H10, 2N plus 2. So 2 times 4 plus 2 is 10. This is the structural formula, CH3, CH2, CH2, CH3. Again, the reason that the central carbons have 2 hydrogens and the outside ones have 3 is this carbon is bonded to 2 other carbons, this carbon is only bonded to 1 other carbon, and every carbon needs 4 bonds. So you have less hydrogens on the central carbons. If you look at the structural formula, expanded out, you'll see it here. And here you have CH3, and here you have CH2, and here you have CH2, and here you have CH3. Okay? And if we were to draw the skeletal formula, CH3, CH2, CH2, CH3. Now let's look at an isomer of this. An isomer is the same molecular formula with a different structural formula. Here we have a methylpropane. Now, whether this is called 2-methylpropane or just methylpropane, I would argue that both are correct. All right. Some people will say that 2-methylpropane is not correct because you can't make anything other than 2-methylpropane. I would argue they're both correct, but I put it in red here. So it could either be 2-methylpropane or simply methylpropane. Usually, you need a number telling you which carbon the methyl group is off of. Anyway, let me explain what a methyl group is before we go too much further. Note that this is also C4H10. But the structural formula is different. It's CH, CH3, 3. Okay, so if we look here, we have a CH right here. And then we have a CH3, a CH3, and a CH3. These molecules will have different melting and boiling points. They will not have different molar masses. Why will they not have different molar masses? Well, they both have 4 carbons and 10 hydrogens. So they're different, but they're the same. And that's what isomers are. They're the same molecular formula with a different structural formula and often different physical properties. Now, are these molecules going to be extremely different? No, they're not going to be extremely different, but they will be somewhat different. So here, if we look at this particular example, we could draw it in this way. CH3, 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 C. And since it's bonded to 3 carbons, it must have 1 hydrogen. And we could also write it in this way, which again is either 2-methylpropane or just methylpropane. Now, let's compare the names. Butane, if we go back to our chart, is the 4-carbon name. But in this case, we're calling this a methylpropane. Why? Because the longest carbon chain is 3 carbons, and 3 carbons, if you'll remember, is propane. Now, what's sticking off of that propane? What's sticking off of that propane is a 1-carbon group. A 1-carbon group is called methane. But when it's sticking off, instead of methane, we call it methyl. We take away the ane, the A-N-E, and we add the Y-L. So we have a 3-carbon group with 1 carbon sticking off, and we call that a methylpropane. One interesting thing to note is that the arrangement of the atoms don't matter. In this case, it doesn't matter. In this case, there's a 4-carbon chain shown in red in each case. So all of these have a longest chain of butane, whether I draw them in this orientation or this orientation or this orientation. The truth of the matter is, one, they can move around, okay? These single bonds allow free rotation, so they can move around. But in 3-dimensional space, the most favored arrangement is tetrahedral. Why? Because we have 1 carbon bonded to 1, 2, 3, 4 things, so the most favored arrangement is for them all to be tetrahedral. That's not to say they can't move, but it is tetrahedral. So when we draw it on a piece of paper, we're not accurately drawing it in 3-dimensional space to begin with. And of course, they can move, so that can change. But also, this, and this are all the same. The take-home message of this is the name of an atom and the properties of an atom depend on the longest carbon chain. Whether it's drawn this way or this way makes absolutely no difference. What matters is the longest carbon chain. Let's look at pentane, C5H12, which has 3 isomers. Okay, the straightforward, if you will, isomer is 5 carbons in a row, pent like pentagon. This one's called pentane because it has 5 carbons. 1, 2, 3, 4, 5. Okay, and the skeletal formula. So we have the expanded structural formula and the skeletal formula. In this case, we have a methyl group sticking off a 1, 2, 3, 4 carbon chain. So this 4-carbon chain is called butane. And sticking off the central carbon is 2-methylbutane. Again, the 2's in red because I could simply call this methylbutane because there's no such thing as 3-methylbutane or 4-methylbutane. All right, I'll show you in a minute why it can't be 3-methylbutane, but you can see why it can't be 4-methylbutane, because if I go 1, 2, 3, 4, and then I put the methyl group, I'm going to have a 5-carbon chain. So 4-methylbutane is pentane. You must call this pentane. You may not call this 1, 2, 3, 4 methyl butane. Because if you did it that way, then every molecule would have an infinite number of names, and the system is set up so that each molecule only has one name. All right, so this is pentane, and this is 2-methyl or just methylbutane. Here's the skeletal formula there. 1, 2, 3, 4 carbons with a methyl group sticking off. Remember, methane is 1. When it's sticking off of a longer group, we call it methyl. Let's look at the third isomer of pentane. In this case, let's count the longest chain. Well, it's 1, 2, 3, or 1, 2, 3, or 1, 2, 3, or 1, 2, 3. And there's probably other ways of counting 3, but no matter what I do, okay, the longest chain I can go is 3 carbons. So there's a typo here. This is not a butane, okay? This is a propane. So this is 2,2-dimethyl propane. Note that the longest carbon chain is 3, and I'm going to use this 3, 1, 2, 3. On the second carbon, there's 2 methyl groups, so I add dimethyl to the name. If it was 3 methyl groups, we call it trimethyl. Again, because there's only one option for dimethyl propane, technically you don't need the 2,2. So you could see either 2,2-dimethyl propane, or you could see just dimethyl propane. Some people will say you can't have the 2,2, which is a reasonable opinion. I would say you could have either, but again, that's just a matter of opinion. It's probably not technically a matter of opinion. They're probably technically correct, but that being said, this only applies to very small molecules, which are important to start with when you're teaching. When you're going to larger molecules, you're always going to need a number to let people know where the methyl groups are. Let's look at this example of 2-methyl or methylbutane. I talked about before that we could have this methyl group on carbon 2. 1, 2 carbons in, we have this methyl group for 2-methylbutane. But what about this? Is this 1, 2, 3-methylbutane? No. And the reason this isn't 3-methylbutane is, who's to say this is carbon 1? If I take this and, like a pancake, I get it with a spatula and I flip it over. If I flip it over, I'm going to get this one. All right? And when I get this one, now this is carbon 1. 1, 2-methylbutane. Note that once I've established that this is butane, all right, this 4-carbon chain, I have to check 1, 2 or 1, 2, 3. Since 2 is smaller than 3, I have to call it 2. Said another way, if I was just checking this one, I would check it 1, 2, 3 or 1, 2. 2 is smaller, I'd call this 2-methylbutane. In this case, 1, 2, 3, 1, 2, 2-methylbutane, or 1, 2, 3, 2-methylbutane. Whichever number is smaller is the number that I need to use in the naming. Let's look at pentane. All right, so these are isomers of hexane, but these are methylpentanes. So in this case, I have 1, 2-methylpentane, or 1, 2, 3, 4-methylpentane. I must call this 2-methylpentane. Also notice this isn't in red anymore. So for molecules even as with only 6 carbons, I now absolutely must number where that methyl group is. Now let's look at this one. This is 3-methylpentane, and these are different because this is 1, 2, 3 or 1, 2, 3. So having it on carbon 2 or carbon 3 is different. Note that if I had it on carbon 4, 1, 2, 3, 4, it would again be 2-methylpentane, because it would be 1, 2 from this side, if you will. So in this case, this is 2-methylpentane, and this is 3-methylpentane. If this isn't making a whole lot of sense, we will do some examples in a few minutes, and then hopefully it will make a little bit more sense. The other thing we can do is we can add halogens. All right, so notice I've added a chlorine and I call it a chloro. If I added a fluorine, I'd call it a fluoro, or a bromine would be a bromo, or an iodine would be an iodo. All right, and I have here propane, 3 carbon chains. Here I have a chloropropane. All right, I have 3 carbons, so it's a chloropropane, and I call it carbon 1 chloropropane, because my choices are 1, 2, 3. So 1 chloro, or 1, 2, 3, 3 chloro. Since 1 chloro is smaller, I call this 1 chloropropane. What about 2? Is this different? Yes. In this case, it's different because here the chlorine is on carbon 2. 1, 2, or 1, 2. All right, so this is 2 chloropropane. What if I put it on the 3rd carbon over? Well, if I put on the 3rd carbon over and it looks like this or it looks like this, it's 1, 2, 3. Wait a second. It's not 1, 2, 3. It's simply 1, 2, 3, 1 chloropropane. So this is this one flipped over, and these are both exactly the same. So I only have 2 isomers here, not a 3rd isomer, because this one and this one are the same and they have the same name. So generally speaking, when we're naming alkanes, we want to find the longest chain and name the base alkane. Then we want to find the groups off of the longest chain, and if they're alkane groups, name them ending in YL. So methane becomes methyl, ethane becomes ethyl, propane becomes propyl. All right, and if they're halide groups, like fluorine, chlorine, bromine, or iodine, we use the halo form of the name, fluoro, chloro, bromo, or iodo. All right, when there is more than one choice possible, number the group with the smallest possible number. If there are multiple groups, use the lowest possible number for all groups and alphabetize the groups in the name. All right, so we're going to use these rules to name these things. So what you're going to need is that sheet with the names of the different groups, because I don't expect you to know that, butane is 4 carbons at this point. So what we have here is 1, 2, 3, 4, 5, 6 carbons. And I'm going to go ahead and circle the longest chain. So if I use my lecture notes here, I find that 6 carbons is called hexane. So the base name of my molecule is hexane. What's sticking off that hexane? Well, the thing that's not in the circle is a methyl group. So this is a methyl hexane. Where's the methyl sticking off? 1, 2, 3, or 1, 2, 3, 4. So my choices are 3-methylhexane or 4-methylhexane. Since 3 is a smaller number, I'm going to call this 3-methylhexane. This is one word, but it's hard to not leave a space accidentally because we write this first and then we write this after it, so you have to guess where the M goes. So this is all one word, 3-methylhexane. All right, let's look at the next one. Let's look for our longest chain. Our choices are 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, which is the same chain. So in this case, the longest chain is 5. If I go to my lecture notes here and I find 5 carbons, I find that a 5-carbon chain is called pentane. All right. Now, what's sticking off the pentane? Well, I again have a methyl pentane. My choices are 1, 2, 3 or 1, 2, 3. Either way, this is a 3-methyl pentane. All right, let's look at the next one. Longest chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 7 is the longest carbon chain. I use my sheet. I find 7 carbons, and 7 carbons is called heptane. So I'm going to go ahead and put the base name of this molecule as heptane. All right. Now, what's sticking off of this longest chain? The nice part about circling these longest chains is you can easily see what's sticking off of it. Well, it's a 2-carbon group. A 2-carbon group is called ethane. So a 2-carbon group sticking off is called ethyl. So this is an ethyl heptane. Now my choices are 1, 2, 3, 4, or 1, 2, 3, 4. So it's 4 either way. So it's a 4-ethyl heptane. I should have mentioned, because I didn't before, I removed the hydrogens from these just because it's easier to see what's going on. But if you were asked, how many hydrogens does this have? The answer would be 3. Why? Because it has 1 bond to carbon and it's got 4 total bonds, so it's got to have 3 hydrogens. This carbon has 2 because it has 2 bonds to carbon, so it must have 2 bonds to hydrogen. This carbon has 3 bonds to carbon, so it must have 1 hydrogen. So you could also figure out how many hydrogens are on each of these things. They're just not shown to make life a little easier as far as seeing it. All right, last one on this page. We need to name this thing. So we need to find the longest chain. 1, 2, 3, 4, 5, 6, 7. All right. So we have 7. We already used a 7-carbon chain. A 7-carbon chain is called heptane. Now, what's sticking off of it? Well, 1, 2, 3 to my first methyl group, or 1, 2, 3 to my first methyl group. So either way, it's going to be a 3, 4, 5. 1, 2, 3, 4, 5, 3, 4, 5, dash trimethyl heptane. All right. So since it's 3 methyls, I call it a trimethyl. If it's 2 methyls, you call it a dimethyl. If it's 4 methyls, it's not going to come up in the ones that we're going to show in this course. Okay. All right. Let's look at some with halogens on them. We have chlorines and fluorines on these different ones. So here, longest carbon chain. So we have the longest carbon chain is the straightforward one. 1, 2, 3, 4, 5, 6. All right. 6 is hexane, like a hexagon. All right. So we have 6 carbons. So now we have to decide our numbering. 1, 2, 3, or 1, 2. So I need to call this 2, 3, 4. Okay, because 2 is a lower number, so I don't want to start on this side. I want to start on this side. Note, you can't start on both sides. You can't call this 1, 2 and this 1, 2, 3. Once you pick a side, once you decide this is carbon 1, you have to number 1, 2, 3, 4, 5, 6. You have to continue in the same direction. All right? Now, I know that it's a 2-chloro and a 4-methyl. Well, methyl starts with an M and chloro starts with a C, and believe it or not, you have to write the chloro first. So this is a 2-chloro, 4-methyl hexane. All right, so we put the chloro first because the letter is C as opposed to M, and that's why it goes first. All right, so let's look at this example here. Here again, the carbon chain that's the longest is the straightforward chain, like that. Okay. So I have 1, 2, 3, 4, 5, 6. This is again a hexane molecule. All right. Now my choices are 1, 2, 3, or 1. So I'm going to pick this side being 1, 2, 3, 4. All right. Now I have a fluoro and 2 methyl groups. And here's where it gets confusing about alphabetization. If I find this to be a dimethyl, I alphabetize based on the M of the methyl group, not the D of the di. So fluoro actually goes first because F comes before M. So I have 1 fluoro, 3, 4. I'm not going to have room for it here. Dimethyl hexane. All right, so I have 1 fluoro, 3, 4 dimethyl hexane. Again, not super important if you know the fluoro or the methyl comes first, but this is basically how we do it. All right, let's look at this last example. So in this example, The longest chain is that one, which is 1, 2, 3, 4, 5. So the base name is this one, is pentane. All right. So what's sticking off of our pentane chain here? Well, we have a fluoro, a methyl, and a chloro. In this case, we have 1 or 2. So this has to be 1. So 1, 2, 3, 4, 5. Again, once I call this 1, I have to number everything in that direction. I can't call this 1 and then come back and call this 2. All right, I have to stick with the direction that I already picked. So in this case, we have 1 with a fluorine and 3 with a methyl and 4 with a chloro. Well, because C comes first alphabetically, I'm going to call this a 4 chloro. Then 1 fluoro. I think that the fluoro might be UO. And then 3 methyl, because M comes last in the alphabet after C and F, so methyl pentane. So this is a 4 chloro, 1 fluoro, 3 methyl pentane. Even this small molecule has this really long name. So as you can imagine, these names are, useful for small molecules, but a lot of things have common names. If you were to name aspirin like this, it'd be 2 lines long worth of names. And some molecules, their names are half a page. So they're not always useful. And there are a lot of common names out there, but this is how IUPAC naming works. That being said, you can use this to name lots of molecules with lots of different functional groups, and many textbooks do give you examples of naming within chapters that talk about different functional groups, and generally speaking, these are some of the easiest questions that you're going to get on an organic chemistry exam, so it's worth your time to learn how to do this, and you can easily apply this to learn the names of other functional groups if you take organic chemistry in the future. So the last thing that I want to talk about is functional groups. So I mentioned functional groups, but now I actually want to talk about functional groups. So there are a bunch of different arrangements of atoms that are commonly found in organic chemistry. One we've already talked about, which is alkanes, which is CN2N plus 2. We can also have alkenes, which have a double bond in them, okay? And these are CnH2n, and they contain a double bond. We can have alkynes, which are not super common in nature, but they actually have a triple bond in them, CN2n minus 2. One of the more famous alkynes is acetylene, which is poorly named because it should be called acetylene, but it's basically a triple bond, and it's used in torches and things for welding and stuff like that. All right. This arrangement of atoms where you have CH at each of these vertices and you have these alternating single, double, single, double, single, double bonds, this is called aromatic. All right. So this is an aromatic molecule. These types of molecules are commonly found in gasoline. All right, so if you put methyl benzene, which is called toluene, it's one of the major components of gasoline. Alcohols, okay, so alcohols are organic functional groups with an OH, and we've all heard of alcohol. Ethanol is the one you drink. Methanol, wood alcohol, is found in things like windshield washer fluid. It's good for cleaning and for lowering the freezing point of windshield washer fluid, but it's poisonous if you drink it. Or rubbing alcohol, which is isopropyl alcohol. Again, it's poisonous to drink, but it's good for cleaning. All right. Ether. Ethers have an oxygen in the middle. Carbon-containing group, O, carbon-containing group. And that's an ether. An aldehyde has this C double bond O bonded to an H. All right. A ketone is very similar. It has a C double bond O, but it has 2 carbon-containing groups. Here, I've represented anything outside here to be carbon-containing groups or an H. In the case of a ketone, they both have to be carbon-containing groups. If they're both H's or even one of them's an H, then it's an aldehyde because these are very similar types of molecules. Carboxylic acids, we've talked about acids before, and we've actually talked about acetic acid. This is the acidic proton, and they have C double bond O, bond OH. and these are common. All right, esters, which are commonly found in different fragrances and things like this. We have a C double bond O, but instead of having an H, we have another carbon containing group. Amines, okay, are one of the two functional groups that contain nitrogen. The amine is bonded to H's or other carbons, all right? If it's only bonded to H's, then it's called ammonia, and that's not an organic molecule because it doesn't have a carbon. But if it has at least one carbon in it, then it's an amine, and these might be hydrogens or they could be carbons, or it depends on whatever the case may be. And then finally, amides. The difference between amines and amides is the presence of the C double bond O. So what I'd like to do now is switch back over to the camera and go through a few different examples of molecules that contain these different functional groups and are actual molecules. So that's basically what we're going to do. It'd be a good idea for you to take a look at this as we do this. I'm not going to take a look at this as we do this, but I'm going to explain them as we go. So let me switch back over to the camera here. All right. So let's look at these molecules, and we're asked to identify the functional group of each molecule. And then after we identify the functional group, because a lot of times if I tell you what it is, it'll give away what the functional group is. I'll tell you what each of these molecules are and why it's important and why you may have heard of it before. Okay. So we have CH3, CH2, OH. So we're looking for molecules with OHs in them. And as we scan our list here of molecules with OH, we see this molecule has an OH and this molecule has an OH. Well, what's the difference between an alcohol and a carboxylic acid? The difference is that this one has a C double bond O attached to the OH and this one does not. So let's look at our actual molecule. Okay, here I do not see a C double bond O attached to my OH. So this one is an alcohol. This particular one is ethanol, which is drinking alcohol, stuff you find in vodka or beer. All right, let's look at this one. CH3, CH2O, CH2, CH3. So we have an oxygen sandwiched between two carbon-containing groups. Let's look over here for oxygen sandwiched in between two carbon-containing groups. Well, an ether is an oxygen sandwiched in between two carbon-containing groups. And an ester is carbon, oxygen, and then another carbon-containing group. Again, what differentiates the ether from the ester? The C double bond O. So in this case, we have a C double bond O directly attached to the oxygen. In this case, no C double bond O. So let's look at our actual molecule again. No C double bond O, only bonded to an O. This one is ether. This molecule is commonly called ether. All right, it's diethyl ether, or commonly referred to as ether. This is a common organic solvent. This molecule is also, if you've heard of someone lighting a cigarette in a meth lab and blowing it up, this is a likely culprit for why that might happen. All right, C triple bond C bonded to two H's. So let's look at our groups. Let's look for triple bonds. Well, if we scan through here for triple bonds, we're only going to find one. All right, so this molecule is an alkyne. All right, so this molecule is an alkyne, and this particular alkyne is called acetylene, the stuff used in welding torches and stuff like that. All right, now we have a molecule with a C double bond O. All right, so we have C double bond O, bond H, bond H. When we go back to our molecules and we look for C double bond O, we're going to find a lot of them. All right, so they're grouped together, but C double bond O, C double bond O, C double bond O, C double bond O. Now, if we recall from our molecule, it only had one oxygen in it. So since it only has one oxygen in it, that illuminates this one. This has two oxygens, and this one because it has two oxygens. So it has to be either this one or this one. I guess it could be this one, but it doesn't have a nitrogen. So it's either this one or this one. If one of the two groups bonded to the C double bond O is an H, it's an aldehyde. It could be both of them or one of them. So if we look here, we have C double bond O bonded to an H. This one is an aldehyde. All right, this molecule is called formaldehyde. All right, the stuff that you've probably heard of before, formaldehyde. All right, so let's look at this one. In this case, I want to focus on what's in the box, all right, because there's multiple functional groups. We have a carboxylic acid here, we have an amine here, but let's focus on what's in the box. This molecule is C double bond O bond N, all right? So let's look here. There's only two molecules that have N's. What distinguishes them is the C double bond O directly attached to the N. We have that. So this is called an amide, the thing in the box. All right. And this is actually a peptide bond because this is glycine and this is glycine, and these two things, this is glycine, and these two things are now linked together through a peptide bond. Note that this molecule continues to have an NH2 and a carboxylic acid, so we can link another one and another one and another one and another one, which is why you can form polymers out of these amino acids, which those polymers could be proteins, enzymes, this kind of stuff. All right, so this one is an amide. Next one, C double bond O, CH3, CH3. Couple things to note. There's no other oxygens, and both the groups on the outside are carbon-containing groups. So when we look here, the only example where there's no other oxygens and both the groups are carbon-containing groups and no nitrogen is a ketone. So this molecule here is a ketone. All right. One thing to note about this one, not a ketane, it's a ketone. That's an O. All right. A ketone. This one is acetone, the stuff found in nail polish remover. So all of these molecules have, everyday uses. And we can identify the functional groups of these real molecules. Let's look at two more examples. And these are examples with multiple functional groups. So this one has this functional group and this functional group and this functional group. So let's take a look at these. Let's do this big one first, this big ring. Well, this one's really easy to spot because it looks exactly like this ring. So this one is aromatic. So this is aromatic. I should note that this molecule we're finding the functional groups of is called aspirin. Here we have a C double bond O bond O. So we have a C double bond O attached to an O. Which functional group has a C double bond O? Remember, our C double bond O's are down here except this one, but this one has a nitrogen, so it's not counting here. And it's attached to an O. C double bond O attached to an O. That is an ester. All right. So here we have an ester. Here. All right. What about this one? C double bond O bond OH. So it's again attached to two O's, but the O is attached to an H. C double bond O bond OH. This is called a carboxylic acid. All right. And you may have heard before that aspirin is acidic. Well, aspirin has a carboxylic acid. If you were to compare this to salicylic acid, which aspirin can be made from, that is much more acidic, okay, and that's used in like acne cream and things like that, and you can't eat that one. But this carboxylic acid is weak enough that many people can tolerate eating this or ingesting it and taking it as a medication that way. All right. We now have an amino acid, glycine. I talked about this one at the beginning of class, or beginning of this lecture, and basically that was this one and this one, all right, and why we need to understand organic chemistry. And this is an amino acid which can, combine, and we talked about a peptide bond in the previous slide. So this has an NH2, which is an amine, and a C double bond O bond OH, which is the same as this one, which is a carboxylic acid. So why this is called an amino acid is because it has an amine functional group and a carboxylic acid functional group. Therefore, it is called an amino acid. So that brings us to the end of the lecture on organic chemistry. This isn't everything there is to know. This isn't everything there is to know about organic chemistry in 1 hour, certainly, but it is the only video for this entire chapter. I'm again leaving the sections about the individual functional groups open, and it does talk about naming those functional groups, but you can take a look at that, and you don't have to go into the naming of those functional groups for this course, but it's there if you want to take a look. Thanks for watching.